Welcome back, everyone. I'm here on page 10 of the chapter 11 lecture note outlines, where we're about to start part 5, which is about heating curves. When I say heating curves, what I mean is we're going to be looking at the different changes in energy associated with changes in the physical state. So if we go from, say, a solid up to a liquid and then up to a gas, we're going to be looking at the way the energy changes as well as the temperature changes through all of those states. So to get started with that, here in part A, the first thing I'm going to introduce to you is something we call Q, which is the heat involved in a process. So heat, which is a measure of thermal energy, we designate by using the symbol Q. Q represents heat or thermal energy. Now, we have a lot of different units that we use for Q that we haven't seen before. So we're going to see these units a few times. Some of these are probably familiar by name to you, such as the calorie, and some might not be as familiar to you, like the joule. So right up here at the top, I start us off with a few conversion factors that we'll use a bit later. Just take note for now that we have something called the calorie with a lowercase c, and I provided the conversion factor between the calorie and the joule. We also have something called the kilocalorie, which is 1,000 of those calories with a lowercase c. This is often used in nutrition with the calorie with a capital C. So if you look on a food product, it lists a number of calories. That's actually a capital C calorie, which is 1,000 of the calories that we're talking about. So let's get started first talking about Q, this units of heat. What is Q exactly? To explain what I mean, let's first relate Q to something we're maybe a little more familiar with, that being temperature. And I'll use the symbol T to represent temperature. So if T is my symbol for temperature, we can represent the change in temperature using the symbol delta T. So if we raise the temperature of a sample of matter, we have to put energy into the system so that we can increase the average kinetic energy of the molecules or the particles in that sample of matter. And by the same token, if a sample of matter cools, so it goes from a higher temperature to a lower temperature, energy must be released. That's because the molecules in that sample are moving to a lower kinetic energy state. Therefore, if temperature goes down, Q would also go down. So we can see from this relationship that temperature and Q are directly proportional to one another. But let's say we needed to know how much energy was actually necessary to change the temperature of a specific substance by some specific amount. Say we wanted to know how much energy was necessary to raise the temperature of a block of metal by 10 degrees or a glass of water by 100 degrees. How could we figure that out? Well, we would need an equation that relates temperature and Q. So instead of having a proportionality between these two, we want an equal sign with some kind of formula to follow. And that brings us to the next subject, which is specific heat. Every substance or material has different heating properties. So in my example earlier, I was talking about water versus metal, right? Metal conducts heat very easily, whereas water does not because of the different properties of those materials. We take this into account by using the letter C to represent something called the specific heat. The specific heat for a substance tells us how much heat energy is needed to actually change the temperature of that substance. So a higher specific heat means it requires more energy for a temperature change than something with a lower specific heat. Now, one note about specific heat is that it is a constant for a given material. So different materials have different specific heats, and of course these are based on their thermal performances or the ability for them to conduct heat when the temperature changes. And in general, we expect things that are better conductors to have lower specific heats than things that are poor conductors, which have really high specific heats. So as an example, let's take a look at this table where I have tabulated a number of specific heats for different materials. We can see water up at the top here with a very high specific heat of over 4,000. Compare that with aluminum, which is down here at 900. Aluminum is a metal which conducts heat very easily and therefore has a lower specific heat. Notice that all of these different materials have different types of specific heats. We even see that if we have the same type of chemical compound, we can still have a different specific heat when that compound is in a different state of matter. So for example, liquid water has a specific heat of 4,186. Compare that with ice and steam, which each have different specific heats as well. So different materials have different specific heats, and the specific heat represents the ability of that material to conduct thermal energy. So let's review what we've learned so far. The energy, or Q, necessary to change the temperature of a substance is directly proportional to that change in temperature. We also know that the energy necessary to change the temperature of a substance is also directly proportional to its specific heat. Now, what else do we need to take into account when we're changing the energy of a substance? Well, that's right. What about its mass? Wouldn't it take more energy to change the temperature of something where we have, say, 100 grams of it versus if we only had, say, 10 grams of it? More stuff means we need more energy to change its temperature. So the energy necessary to change the temperature of a substance is also directly proportional to its mass. We can write this as a mathematical expression at this point, where we represent energy Q on one side and the mass, the specific heat, and the change in temperature on the other side. And in this way, we get an equation that we can use to help us calculate energy associated with temperature changes and different types of materials, which is Q is equal to M times C times delta T, or Q is equal to MC delta T. Now, this makes sense, right? The more stuff we have, the higher the Q. The different type of stuff we have will change the Q as well, and the change in temperature will also affect Q. So a greater change in temperature will mean more energy, and a lower change in temperature will mean less energy. So with this equation in hand, where we can calculate Q for different types of substances, let's go to the next page and try out a few examples. So if we read through this first example problem, we see we have 35.2 grams of aluminum, and we're given the value of C for aluminum, which is 0.895 joules per gram degrees Celsius. That's one type of unit system that we'll see for a specific heat. Anyway, this aluminum, this block of aluminum, is heated with 291 joules of energy. And the starting temperature is given to us as 46.3 degrees Celsius, and we're being asked, what will be the final temperature? So we want to approach these types of problems much in the same way that we approach the gas law problems. We're going to write down all of the parameters that were given next to the variables and then identify the missing parameter that we can hopefully solve for using the equation. So let's put a line down for each of the parameters: heat, mass, C, and change in temperature. Now let's go back and read through this problem and see if we can pull out those different parameters. So we see if 35.2 grams of aluminum, that there is our mass. So let's write 35.2 for our mass. That's grams. And then we're given C for aluminum, which is 0.895 joules per gram degree C. And then we're told that is heated with 291 joules. That's our energy, or Q. We're also told that the starting temperature is 46.3 degrees C, but we don't know what the final temperature is. So that means we don't have delta T, but we have the starting temperature. Now, in general, if we want to find delta T, it's going to be equal to the final temperature minus the initial temperature. So as we can see, the missing parameter here is our delta T. That means we need to rearrange our Q is equal to MC times delta T to solve for that delta T. If we do this, we see that delta T is equal to Q divided by M times C. Now we can rewrite this by plugging in the parameters that we've written down here on the left. So we have Q, which is 291 joules on the top, divided by 35.2 grams, that's the mass, times 0.895 joules per grams degrees Celsius. Also, we should look at the unit analysis for this before we actually solve it. So notice that grams would cancel grams here, and then joules being divided into joules goes here, and then we're left with the inverse of degrees Celsius, which will just be equal to degrees Celsius, which agrees with the fact that we're trying to solve here for a temperature unit, which would be degrees Celsius. So go ahead and pause the video, get your calculator out, and put these numbers in and see what value you get. So for the calculated value here for delta T, we get 9.24 degrees Celsius. Now let's recognize what this is. It's the change in the temperature for this system. Now, of course, this is just the change in temperature. How do we actually find the final temperature? Well, we go back to our equation over here on the left, which shows us that delta T is equal to the final temperature minus the initial temperature. So because we know the change in temperature and we know the starting temperature, we can find the final temperature just by rearranging this. As such, we see that the final temperature is equal to the change in temperature plus the initial temperature. And if we do that, we get 55.5 degrees Celsius. So it turns out if we know the energy applied to a system and the mass of that system, as well as its heating properties, we can figure out what temperature it will go to. Let's look at another problem down here to see what else we can do with this Q is equal to mc times delta T. If 20 grams of water, and we're given this specific heat there for water, which is at 25 degrees Celsius, is heated to 100 degrees Celsius, how much heat was required to actually do this? So what we're being asked for here is the amount of energy necessary to change the temperature of a substance. Let's start off again by writing out the equation, Q is equal to mc times delta T, and then also write out a space for all of the different parameters, and let's fill in those parameters with the values we're given in this problem. So looking back through this sentence here for the problem, we see we're given 20 grams of water. That's our mass. So let's write that next to M. And then we're given this C, which is 4.184 joules per gram degree C. That's our C value. And then we see the temperature parameters here. It goes from 25 degrees Celsius to 100 degrees Celsius. The delta T there is that final temperature, which is 100 degrees Celsius, minus 25 degrees Celsius, or 75 degrees Celsius is the delta T. Now, how much heat was required for this? We're being asked here to solve for Q. So to solve for Q, or our heat energy parameter, we just need to plug in the mass, the specific heat for water, and the change in temperature. Now, once you have all these values written out, let's do a quick unit analysis. We see grams cancels into grams and degrees Celsius cancels into degrees Celsius. And what we're left with there is the unit of joules, which is the unit for heat energy that we often use when we're not using the calorie. So what I want you to do is pause the video and see if you can get the correct value for this. And don't forget about significant figures. So hopefully you had a chance to calculate that, and you see that you get 6,300 joules. And that's two significant figures. Notice our temperature unit only has two significant figures, so therefore we're limited to two sig figs for our answer as well. So now that we know how to calculate the energy that is necessary to change the temperature of a substance by a specific amount, we can move on to the next topic, which is learning about different energy changes when we are moving through different states of matter. So what we've looked at so far is when we just have one state of matter and we're changing its temperature. What happens if we took something like ice, solid ice, at say minus 20 degrees Celsius, and then we warmed it up to its melting point, melted it, and then we warmed that liquid water up to its boiling point, boiled it, and then vaporized all of it? How do we determine Q in these situations where we are going through different states of matter? Well, determining the energy involved in these types of physical processes, we need to take into account two different types of changes that we have going on. The first type of change is represented on this graph with sloping lines. Notice that on this graph, I have temperature represented on the y-axis and energy represented on the x-axis. Sloping lines on this graph represent changes in both temperature and in energy. These would be things like heating up a solid, or heating up a liquid, or heating up a gas. When we're doing that, we're not only changing the temperature of that sample of matter, but we're also changing its energy. Now, another type of change that we haven't learned about so far are the regions I've shown here shaded in blue, namely the conversion from the solid state to the liquid state, or from the liquid state into the gas state. These changes, going from solids to liquids or liquids to gases, do not involve a change in temperature, but they do involve a change in energy. So we need some way to determine the amount of energy involved in these melting and vaporization processes. Let's look at melting/freezing first. So when we melt something, of course, we're turning the solid into the liquid state. And when we're freezing it, we're turning the liquid back into the solid state. There is a change in energy involved in this process. When we take, say, water in the solid state, otherwise known as ice, and we melt it, we have to put energy in. Let's call this delta H, this amount of energy that we have to put in. Now I'm using a different symbol here. I'm using the symbol H to distinguish it from Q. That's because this is a different type of energy change. This involves a change in state, and for that reason we use a different symbol to denote it. Now, if I converted the liquid water back into solid water or ice, I would have to remove energy, and it would be the same amount of energy, but in the opposite direction. So let's call that negative delta H. Now, this change in energy between these two states, between the solid state and the liquid state, we refer to this change in energy as the heat of fusion. Fusion being taking something and fusing it or putting it together. And we give it the symbol delta H with a little subscript there, FUS, to represent it as fusion. Now, where is this heat of fusion used on one of our heating curves that I've shown over here? Well, that's right. It's right here on the phase change between solid and liquid. So this is where we use this heat of fusion, delta H fusion, right there. Now, to calculate Q for this region where we're going from the solid to the liquid state, we're not going to use a change in temperature to help us with that Q calculation because there simply isn't a change in temperature. There is a change in energy, however. So what we do is we write down Q and we say that instead of it being equal to the mass times the specific heat times the change in temperature, it's just the mass times this delta H with the fusion right there. So if we want to know Q for this area right here for this melting, that's how we find it. It's equal to the mass times delta H fusion. Now, what about this region of the graph over here, the vaporization stage, where we're going from the liquid state to the gas state? How do we calculate that energy? Well, it's very similar to what we did for melting and freezing. We find Q by multiplying the mass of the material that's undergoing vaporization or condensation by its heat of vaporization. The heat of vaporization, or delta H vape, is analogous to the heat of fusion that we saw going from the solid state to the liquid state. So if we have some liquid water that is at its boiling point and we want to vaporize that water, we add a small amount of energy. This energy is the heat of vaporization. That amount of energy is the amount of energy necessary to separate the molecules that have their hydrogen bonds in the liquid state into completely separate molecules that are now no longer bound to one another by any sort of intermolecular forces. Again, this is called the heat of vaporization, and is the amount of energy necessary to transform the liquid at its boiling point into a gas. The heat of vaporization also represents the amount of energy that would need to be removed from a system if we were to convert that system from the gas phase to the liquid phase. So, sort of take home from this part of the lesson is that we have heat of fusion and heat of vaporization. Those are the energies that are involved in the transition between the phases, either solid to liquid or liquid to solid, or for the heat of vaporization, it's between a liquid and a gas. So let's go to the next page where we can put all of this together. So let's summarize what we've just gone over about changes in state and changes in temperature and how we determine the energy of those different changes. Suppose we have a solid that we're going to melt and we want to measure the energy involved in not only raising the temperature of the solid up to its melting point, but also the amount of energy necessary to actually melt it. So we're going to break this into two parts. This first part that I have shown here, we're changing the temperature of the solid from some lower temperature to a higher temperature. To calculate the energy involved in this step, which is called Q1, we multiply the mass of the solid times its specific heat times the change in temperature. And that brings us to the second phase of this energy change, which is the actual melting part, where we go from the solid at its melting point to the liquid at that same melting point. This energy, Q2, is equal to the mass times the heat of fusion. So at this point, we've determined the amount of energy necessary to raise the temperature of the solid up to its melting point and the amount of energy necessary to melt that solid. Now, what about the amount of energy necessary to boil the liquid and then vaporize it? Well, for heating the liquid up to the boiling point, we're going to find the energy there, which is Q3, is equal to the mass times the specific heat for the liquid times that change in temperature. After the liquid has been heated up to its boiling point, we can now calculate the amount of energy necessary to vaporize it. We can find this energy by multiplying the mass of the sample that we're vaporizing by its heat of vaporization. Now, if the vapor temperature is also increased, we might need to calculate that energy as well. To do that, we would find Q5 here, which would just be the mass times the specific heat of the gas times the change in temperature by which we are increasing or decreasing the temperature of that gas. So if we look at this entire process, the total energy involved in taking a solid all the way through the gas phase involves a number of energies. These are Q1 through Q5, and if we summed all of them together, we would find the total Q necessary to accomplish that process. Now, just to reiterate that point, sloping lines on this graph represent changes in temperature as well as energy, but temperature is the key word there. Because these parts of the process involve a change in temperature, or delta T, the formula that we use to calculate the energy must also involve a change in temperature, or delta T. So if we have a change in temperature, we need to make sure we use this formula. Q is equal to m times c times delta T. Now what about the other part of the graph, the flat lines? The flat lines represent a change in state. Because there's no change in temperature, we don't use a formula for Q, which has a delta T in it. Instead, we use the formula mass times the heat of fusion or the heat of vaporization, depending on what state the matter is in. Okay, so while it might seem like a lot of information, realize we're really only using two different equations. We're either using the equation that involves delta T or the one that doesn't. And it's either we're heating something or we're changing its state. So depending on the situation we're in, we're going to choose which equation of Q to use, and the rest is just plugging in the values and getting the right numbers out. Let's go to the next page and try out a real example. Okay, so let's take a look at this problem. It says how much energy is required to heat water from 50 degrees Celsius to vapor at 110 degrees Celsius. The first thing to note is there is no mass given to us here. And that's actually a mistake. So I need to provide you with the mass of water that we're dealing with. Otherwise, we have no idea what Q would be for any of these different steps. So let's assume we have 100 grams of water. So let's write down 100 and put a little decimal point there with grams. That way we have three significant figures. Now what I want you to do is I want you to pause the video, and the first thing I want you to do is draw a graph, kind of like the one I showed on the previous page, that shows what are the different stages that we're going through with this example, and what are the different Qs that we're going to need to calculate. So go ahead, pause the video, and see if you can draw the graph that we're going to use here. So the first thing we want to do on our graph is show some of the temperatures points that we're going to get to. So we're starting at 50 degrees Celsius, and we're going to heat that water all the way up to a vapor at 110. But let's not forget that before that liquid water can get to 110 degrees C, it has to go through a phase change. And that phase change happens at the boiling point for water. So we're going to go from 50 degrees C up to 100 degrees Celsius first. So the first thing we're going to show on our graph is this change from 50 degrees Celsius up to 100 degrees Celsius. This would be a delta T of 50 degrees, and Q1 would be equal to the mass times the specific heat of liquid water times that delta T of 50 degrees Celsius. All right, now what's the next step? The next step is we're going to transform the water, which is currently at its liquid state at the boiling point, into the vapor phase at that same temperature. As this is our second energy, I'm calling it Q2, and it is equal to the mass of the water times its heat of vaporization. Now in the last step of this process, we're raising the temperature of that vapor from 100 degrees Celsius to 110 degrees Celsius. This is our third energy, or Q3. We can find Q3 by multiplying the mass of the water times the specific heat of water vapor times the change in temperature, which here is 10 degrees Celsius. So let's go ahead and calculate Q1, Q2, and Q3. And to help us with this, I'm going to put a table here which has the specific heats and heats of fusion / heats of vaporization for water. So this would be a good time for you to pause the video and see if you can come up with the right values for Q1, Q2, and Q3 using this table and the equations we've shown on our graph to the left. So for Q1, we're looking at raising the temperature of liquid water from 50 degrees C to 100 degrees C. To calculate this, we're going to take 100 grams, that's our mass of the water, and we're going to multiply it by the specific heat of liquid water. We find that on the table as 4.184 joules per gram degrees Celsius. Why do we use the specific heat of liquid water? Well, we're using the specific heat because we're changing the temperature from one point to another. That's when we use specific heats. Why liquid water? Well, because at 50 degrees C to 100 degrees Celsius, we're in the liquid phase until we vaporize it. The calculated value we get for this is 20920. A quick unit analysis for this shows that grams cancels with grams and degrees Celsius cancels with degrees Celsius, and we're left with the units of energy, which is joules. Now, because I'm going to be using this Q1 value when I add Q1, Q2, and Q3 at the end, I don't want to do any rounding at this stage. Instead, I'm just going to put a line underneath the digits which are significant now, so that at the end, when I add all this together, I know how many digits I really should have. Okay, so now let's do Q2 and Q3, and then we're going to add all of those together. So when I'm calculating Q2, I take the mass of the water, which is 100 grams, and I'm multiplying that by the heat of vaporization. So we see the heat of vaporization down here, and that's the value I'm using here. When we do that calculation, we have three significant figures because each of these terms has three significant figures. So I'm just going to underline those significant figures here in Q2. And of course, the units here are joules because grams here cancels with grams here. Now let's move on to Q3. Q3 involves a change in temperature, so I need to use the formula M times C times delta T. The mass is 100 grams. I have to use C here, but the C value is actually not on this table. I provided that the specific heat of steam or water vapor is 2.16 joules per gram degrees Celsius. We multiply that by the change in temperature, which is 10 degrees C, and the value we get is 2,160 joules. That has three significant figures. Now what we're going to do is find Q total by adding Q1, Q2, and Q3. When we do that, we get the calculated value 249,080. Now we have to round this down to 249,000, and that's units of joules, because the 9 there in the thousands position is the least significant digit that we can have. This can be determined by looking at Q1, Q2, and Q3, and noticing that in the 1000ths place for 226000, that's our third significant digit in Q2, that's our least precise value. So that's what we can express our answer over here for Q total out to as well. So that's how we compute the energy, or Q, for a process that involves not only changes in temperature, but changes in state. With that, I will wrap up this lesson and the Chapter 11 lecture note outline packet. Please let me know if you have any questions, and I will see you soon.